Voyager 1 is not dead, but NASA has begun turning it off, not all at once, not suddenly, one instrument at a time. In 2026, engineers made a decision that no one wanted to make. They powered down one of Voyager's scientific instruments, not because it failed, because they needed the power. The spacecraft is now so far from Earth that a command sent from our planet takes about 23 hours just to reach it. Somewhere beyond the edge of the solar system, Voyager 1 is still awake, but it is surviving with less and less of itself every year. Its nuclear power source grows weaker every year. The engineers on Earth must choose what to keep alive and what to let go dark. It left Earth in 1977. No one alive today will ever see it return. And yet tonight, at this exact moment, it is still transmitting a signal so faint that only the largest antennas on Earth can hear it, a whisper from interstellar space. NASA is still listening, but they know what is coming. Some instruments will go quiet, one by one, as the engineers on Earth do everything they can to keep it flying. Tonight, we follow those final years, the instruments, the power, the signal, and the quiet decisions that decide how long Voyager 1 can keep speaking. And now, let's begin. It helps to think about what Voyager 1 actually is, not as a spacecraft, as something closer to a body, a very old body, a very long way from home, trying to stay warm and keep its eyes open. It has instruments, sensors that measure the environment around it. It has a transmitter, the one system that sends signals back to Earth. It has receivers, so it can hear the commands we send from the ground. It has attitude control thrusters, tiny jets that keep its antenna pointed at Earth. If the antenna drifts, the signal is lost, and it has heaters. This is the one most people don't think about. Out beyond the solar system, the temperature around Voyager 1 is only a few degrees above absolute zero, almost as cold as space can get. The spacecraft's internal components, its electronics, its cables, its instruments, were not designed to survive that kind of cold unprotected. So small electric heaters keep the most critical parts just warm enough to function. Turn off a heater to save power, and you risk freezing, something that cannot be replaced. Turn off an instrument to save power, and you lose a sense, but the body keeps going. Every instrument that goes dark is one less way Voyager 1 has of knowing what the universe around it contains, not a catastrophe, but a narrowing, a slow, careful narrowing of what the spacecraft can still perceive. The team at JPL has been managing this narrowing for years. They have models, projections, a careful accounting of how much power remains and which systems can no longer be sustained. The question is always the same. What does Voyager 1 need most, right now, to keep going? For a long time, one of the answers was the LC-PEEP, the low-energy charged particle instrument. For nearly 49 years, it had been listening, not to sound. There is no sound in deep space to particles, ions, electrons, cosmic rays, things moving through the space between stars that carry information from places no spacecraft has ever reached, even in interstellar space, the vast quiet beyond our sun's reach. The lessee was still measuring. It was one of the ways Voyager 1 could feel the environment around it, a sense. And on April 17th, 2026, that sense was switched off, not because it failed, it was still working. The command that left Earth that morning was not a rescue. It was not an emergency. It was a goodbye to one of the last ways Voyager 1 had of sensing the space around it. The team sent the command. Then they waited about 23 hours. When confirmation came back, the LEC was silent. Voyager 1 kept flying. It always does. To understand why that choice had to be made, you need to understand how Voyager 1 stays alive. It does not have solar panels. Out where Voyager travels, the sun is so far away that its light is almost nothing, a faint star among other stars. Instead, Voyager 1 runs on heat, 3 small nuclear power sources, quietly producing heat. For nearly 50 years, slowly fading year after year, the material inside them is plutonium-238. That material slowly decays. The decay produces heat, and that heat becomes electricity. No combustion, no moving parts, just steady, slow, invisible decay, producing just enough power to keep a spacecraft alive at the edge of everything. In 1977, those RTGs produced about 470 watts. Now, nearly 5 decades later, only a few hundred watts remain, and the output continues to fall by about 4 watts every year, 4 watts gone every year, and never coming back. This is not a malfunction, it is physics. The decay was always going to slow. The engineers knew this the day they built the spacecraft. They planned for it. They stretched every watt as far as it would go. But eventually, the numbers become a choice, and the choice is always the same. What do we keep? What do we let go quiet? This is why Voyager 1 is not simply aging. It is being carefully reduced, one system, one instrument, one final signal at a time. There is a number that stays with you once you hear it. Not minutes, about 23 hours. That is how long it takes for a signal traveling at the speed of light to reach Voyager 1. The speed of light, the fastest thing in the universe, and it still takes nearly a full day to get there. Then, after the command arrives, the team waits again, another 23 hours, for the confirmation signal to travel back. 2 days for a single exchange. Hello, I hear you. This is not a conversation. It is something slower than that, something closer to leaving a message. In a place you are not sure, Anion will find. Think about what that means. For the engineers who sent it, they could not watch it happen. They could not see the instrument power down in real time. They sent the command into the dark, went home, slept, came back the next morning, and waited for the universe to write back. When the confirmation finally came, a faint signal, crossing more than 15 billion miles of mostly empty space, it arrived not as a voice, not as an image, but as data, numbers arranged in a pattern that told them it worked. The LESP is off. Voyager 1 is still flying. For the engineers who have spent years, sometimes decades, working on this mission, that confirmation is everything. It means the spacecraft is still there, still responding, still alive, in the only way a spacecraft can be alive. Sending, receiving, flying. One instrument quieter than before, but still flying. The decision to power down the LESP did not come quickly. These decisions never do. The team at JPL has been managing Voyager 1's declining power for years. They have spreadsheets, models, projections that map out how much power will be available in the months and years ahead, and which systems will need to be adjusted, cut, reduced, or eventually turned off to keep the mission alive. It is slow, careful work, the kind of work that doesn't make headlines most of the time. Engineers sitting with numbers, running scenarios, asking the same quiet question over and over. What does Voyager 1 need most right now to keep going? For a long time, the EECP was part of the answer. It was measuring the particle environment of interstellar space, a region of the universe that no human-made object had ever entered before Voyager 1. The data it sent back was genuinely new. Details science had never measured this way before, but power does not care about discovery. Power is a number, and when that number gets small enough, something has to give. The engineers made their recommendation. The mission managers agreed. A date was chosen, April 17, 2026. A command was written, and then it was sent. What stays with me, what I find myself thinking about, is not the technology, it is the people, the ones who have worked on this mission for 10, 20, 30 years. Some of them were not yet born. When Voyager 1 launched, they inherited this spacecraft, the way you inherit something from a generation before you. Something old, something still working, something that needs care, and they have given it that care, adjusting, calculating, protecting, the way you care for something. You know you cannot keep forever, but are not ready to let go of yet. The LSEP is quiet now, but the mission continues. Voyager 1 is still out there, still transmitting, still, in its own way, reaching back toward us across the dark. Voyager 1 was not built to last this long. No one expected it to. When it launched on September 5, 1977, the mission was designed to last perhaps 5 years, maybe a little longer, long enough to fly past Jupiter, long enough to fly past Saturn, long enough to send back photographs and data that no telescope on Earth could ever collect. That was the plan. 5 years, a handful of planets, then silence. What happened instead is one of the quietest miracles in the history of exploration. The spacecraft kept going, not dramatically, not all at once, just steadily, day after day, year after year, decade after decade. It reached Jupiter in March 1979. By that point, it had already been traveling for more than a year and a half. What it found there was not what anyone expected: the Great Red Spot. A storm larger than the entire Earth, was more complex than models had predicted. Bands of cloud in the Jovian atmosphere moved in opposite directions, creating shear lines that generated smaller storms, spiraling down into the depths of a planet with no solid surface to stand on. Jupiter's moon Io was volcanically active. No one had known that, not until Voyager 1 flew past and looked back. The images it sent showed volcanoes erupting in real time, plumes of sulfur reaching hundreds of kilometers green to the thin atmosphere above. It was the first time we had ever seen an active volcano anywhere other than Earth, and we saw it because a small spacecraft happened to look at the right moment, at the right angle, as it flew past at high speed. on its way to somewhere else. Science works that way sometimes. You plan for one thing, and the universe shows you another. Then Voyager 1 continued, past the asteroid belt, past the scattered light of the inner planets, deeper. It reached Saturn in November 1980. Saturn's rings were more intricate than anything we had imagined, not a few broad bands, as telescopes on Earth had suggested, but thousands of individual ringlets, some smooth, some kinked, some braided in patterns that defied simple explanations. Scientists called some of them braided rings and struggled for years to understand the gravitational mechanics that produced them. Titan, Saturn's largest moon, turned out to have an atmosphere, a thick, hazy atmosphere of nitrogen and organic compounds, more like Earth's early atmosphere than anything else we had ever found in the solar system. When Voyager 1 flew past Titan, it dipped below the expected horizon, its radio signal passing through the moon's atmosphere. Before reaching Earth, scientists measured the signal's distortion, and from that distortion, they calculated the composition and density of an atmosphere around a world they had never touched. Remote sensing, science done at a distance, through inference and measurement across the cold dark, between worlds, not what we had expected, never what we expected. After Saturn, the trajectory of Voyager 1 curved upward, out of the plane of the solar system. There were no more planets to visit. Some missions might have ended there. Voyager 1 did not. It just kept flying, away from the sun, away from the planets, away from everything familiar, into a region of space that had no name yet, because no human-made object had ever been there. For years, it flew in silence, sending data, receiving commands, consuming power, getting farther. The team at JPL kept watch. They adjusted its trajectory. They updated its software from billions of miles away. They coaxed every remaining watt into something useful. In 1998, Voyager 1 overtook Pioneer 10 as the most distant human-made object in the solar system. At that moment, it became something new, not just a spacecraft on a mission, but the farthest thing we had ever sent, the farthest extension of the human since presence in the universe. And still it kept going. When a backup thruster failed in 1980, engineers switched to a different system. When the primary radio receiver failed in 1988, they adapted. When the power levels dropped below what was originally planned, they found ways to work with less. This is not the story of a machine that got lucky. It is the story of people who refused to stop caring about something they had sent into the dark. Voyager 1 is still alive today because of physics and because of engineering and because of something harder to put a name to, a kind of patience that runs very deep, the patience of people who are willing to wait 23 hours for a reply, who are willing to spend a career listening to a signal that gets a little fainter every year, who are willing to let go of one instrument so that the rest can keep going a little longer. In 1977, it was a machine. After nearly 50 years, it is something else, something that is hard to describe without sounding like you mean more than you do. But tonight, if you are lying somewhere quiet and the room is dark and there is nothing demanding your attention. It is enough to know that somewhere out there, an object the size of a small car and is still moving through the dark, still sending, still flying, still farther than anything we have ever made. There is something in that worth sitting with. The universe is very old, older than any number that fits comfortably in the mind, 13.8 billion years. Since the first moment of expansion, 13.8 billion years of stars being born, burning through their fuel, exploding or cooling or collapsing, 13.8 billion years of matter taking different shapes, clouds of gas, then stars, then planetary systems, then, in at least one place, life, and out of all of that, out of all those billions of years and billions of stars and incomprehensible distances, we are here in this moment on this planet, and we have managed in the last 5 decades to push one small machine past the edge of our solar system. That is, by any measure, an extraordinary thing. The nearest star to our sun is about 4.2 light years away. Voyager 1's traveling at its current speed would take about 75,000 years to reach it. If it were headed in that direction, which it is not, it is traveling in a different direction entirely, toward the constellation Ophiuchus, then eventually the constellation Camelopardalis, and the stars it will eventually pass near are tens of thousands of years away. This is not a discouraging fact. It is a clarifying one. It tells us something true about the scale of what we live inside. We built the fastest machine in history. We gave it the best power source we could. We launched it with the best trajectory available, and it will take longer than our civilization has existed so far just to pass near another star. The universe is large, we are small inside it, and Voyager 1, our farthest, most distant creation, is a reminder of both things at once. It's how far we have reached and how much farther there is to go. Rest in that thought for a moment. There is no rush. The spacecraft is still flying, and you are here now in this moment, which is the only moment that is ever available. The stars outside, if you could see them through the ceilings, through the walls, past the light pollution of wherever you are, they are still there. Every one of them a sun, every one of them possibly surrounded by worlds. Voyager 1 is headed toward the space. It's between some of those suns. It will never arrive, but it is going. And that is enough. Right now, somewhere in the California desert, a dish antenna is pointing at a fixed point in the sky. It is enormous, the kind of structure that looks like it belongs in a science fiction film. And it has been pointing at that same patch of sky for a very long time. It is part of the Deep Space Network. 3 complexes spread around the world. In California, in Spain, in Australia, is positioned so that as the Earth rotates, at least one of them can always see Voyager 1. The signal they are listening for is extraordinarily faint. When Voyager 1 transmits, it does so using about 20 watts of power, about the same as a dim light bulb. That signal leaves the spacecraft and spreads outward in all directions, growing thinner and thinner across billions of miles of space. By the time it reaches Earth, the power that arrives is the power then a billionth of a trillionth of a watt. There is no unit of measurement in everyday language small enough to describe it easily. It is not a sound. Space is silent. It is a radio wave, an electromagnetic whisper, carrying structured data in a pattern that engineers designed nearly 50 years ago. The dish in California catches what it can. It amplifies the signal through layers of electronics, ones designed to hear something almost too quiet to hear at all. And then it begins the long work of interpreting, separating the signal from the noise, finding the pattern in the statics, reading the numbers. This process is not automatic. It requires careful attention. Teams of engineers and scientists who understand both the mathematics of signal processing and the specific language that Voyager 1 speaks, a language that was designed on Earth in the 1970s and has been spoken quietly, faithfully, across an increasing distance ever since. What does the signal say? It says, "I am still here. My systems are running. Here is the temperature inside the spacecraft. Here is the voltage from the RTGs, and here is the status of the instruments still online. Each packet of data is a report from the edge of everything, a status update from the most distant outpost humanity has ever maintained. And when the engineers at the Deep Space Network receive it, when they confirm that the pattern is intact, that the numbers make sense, that Voyager 1 is still responding, there is, I imagine, something very quiet that happens in that moment. Not celebration, not drama, just the particular satisfaction of knowing that something you are responsible for is still out there, still okay, still sending. The Deep Space Network was not built for Voyager alone. It listens to dozens of spacecrafts spread across the solar system, Mars orbiters, probes around Jupiter and Saturn, telescopes in space, landers on distant moons, all of them sending signals, all of them requiring attention. But Voyager 1 holds a special place in the schedule, not because it is the most scientifically active. It is not anymore, but because it is the farthest, because it is, in a very real sense, the most alone, and because the engineers who listen for it understand that there will come a day when they listen and hear nothing. That day has not yet come. Tonight, the antennas are still pointing, the signal is still arriving, faint, yes, stretched thin across more than 15 billion miles, but intact, still carrying its quiet report, still saying, "I am here." The Goldstone facility in California, one of the 3 Deep Space Network sites, has a 70-meter antenna, 70 meters from the ground to its apex, taller than a 20-story building, and it needs to be that large to hear a signal that carries less power than it takes to run a nightlight. It's the precision required to point that antenna at a spacecraft more than 15 billion miles away is extraordinary. Voyager 1 covers roughly 1.5 million kilometers every day. The antenna tracking team must continuously calculate where the spacecraft is and will be accounting for the movement of both the spacecraft and the rotating Earth. Beneath the dish, it is mathematics applied to the problem of listening across an almost incomprehensible distance, and it works. Every day it works. The signal arrives. Every's eyed. The data is decoded, and somewhere in California, in Spain, in Australia, a group of engineers knows that Voyager 1 is still flying, still in its own way, cat calling home. The sun does more than shine. It breathes in every direction at all times. The sun releases a stream of charged particles, protons, electrons, and other fragments of atomic matter, moving outward at hundreds of kilometers per second. This is called the solar wind, and the solar wind does not stop at Mars or Jupiter or Saturn. It continues outward, pushing against this interstellar medium. that fills the space between stars. As it pushes, it creates a boundary, invisible boundary, of vast invisible bubbles surrounding our entire solar system. This bubble is called the heliosphere. Inside it, the environment is shaped by our sun. The solar wind dominates. The magnetic field is our sun's field. The particles are our sun's particles. Everything, in some sense, still ours, outsider it. The environment belongs to something else, to the galaxy. The boundary between these two regions, the place where the solar wind finally runs out of strength, is called the heliopause. No human-made object had ever crossed it until Voyager 1 in August 2012. After 35 years of flight, Voyager 1 passed through the heliopause and entered interstellar space. The first time in history, the instruments on board registered the change. The density of particles around the spacecraft increased abruptly. The magnetic field shifted direction. The solar wind, which had been a constant companion for 3.5 decades, grew quiet, and Voyager 1 flew on into a region of space where no human-made object had ever been. What is it like out there? Not empty, not the featureless void of science fiction. The interstellar medium is thin, far thinner than the best vacuum we can create on Earth, but it is not nothing. It contains hydrogen, helium, traces of heavier elements forged in stars that died before our sun was born. It contains magnetic fields, the ancient, tangled remnants of galactic forces that have been slowly shifting. For billion contains cosmic rays, high-energy particles, accelerating across the galaxy from sources we are still trying to identify. Voyager 1 is moving through all of this, slowly, by cosmic standards, about 17 kilometers per second relative to the sun's, fast enough that it will reach the vicinity of another star system, A79 3888, in about 40,000 years, not close enough to enter it, just close enough to pass by. Ship with no port, moving through the galaxy, not because anyone planned this part of the journey, but because there is nothing left to stop it, and the instruments on board, the ones still running, are still measuring, still reading the environment that no one had ever measured before, still sending the data back. Even now, even with the LCP quiet, Voyager 1 remains the only object in the history of science that has ever made direct measurements from interstellar space. There is nothing else like it, not anywhere. Before Voyager 1 crossed the heliopause, scientists had theories about what interstellar space would be like. They had models, predictions, estimates based on indirect measurements. What Voyager 1 found confirmed some of those predictions and contradicted others. The density of the interstellar plasma was higher than expected. The magnetic field outside the heliopause was oriented differently than some models had suggested. The transition zone, the region just inside and just outside the heliopause, turned out to be more complex, more layered, more interesting than anyone had fully anticipated. There was a region just inside the heliopause where the solar winds slowed dramatically, becoming turbulent and unpredictable before finally giving way to the calmer conditions outside. Scientists had predicted this region. They had named it the heliosheath, but the details of what Voyager 1 found there, the actual measurements, the actual numbers, were different from the predictions, not completely wrong, but different enough to require revision. That is how science advances, not in sudden revolutions, or not only in sudden revolutions, but in this slower way, in corrections, in refinements, in the gap between what we thought and what we found. Voyager 1 has spent decades closing those gaps. Science worked this way. You make your best predictions, you send something into the unknown, and the unknown writes back, sometimes with confirmation, sometimes with surprise, always with more questions than you started with. Voyager 1 has given us decades of answers, and in doing so, it has given us decades of new questions. That is the work of exploration, and tonight, somewhere out there, beyond the sun's reach, a small machine is still flying, still asking questions. By its very presence, still moving through a place no one had ever been, reporting back on what it finds. When most people imagine the space between stars, they imagine nothing, absolute darkness, perfect silence, it's emptiness without end. And in one sense, they are right. The distances are so thin that for almost any practical purpose, interstellar space is as close to nothing as anything in nature gets. But Voyager 1 has taught us that almost nothing is not the same as nothing. The interstellar medium, the environment Voyager 1 now moves through, is a real place. It has structure. There are regions where the density of hydrogen atoms is slightly higher. There are long, slow oscillations. In the magnetic field, waves that propagate across light years of space from disturbances that happened long ago. In places far away, there are electrons, plasma waves, ripples in the charged plasma that Voyager 1's instruments detected and sent back to Earth. When scientists converted those plasma wave measurements into sound, into something a human ear could perceive, the result was eerie, not music, not signal, a kind of low shifting tone, the sound of the interstellar medium, vibrating around a small spacecraft, moving through it at 17 kilometers per second. No one had ever heard anything like it. There had been no way to hear it before. Voyager 1 made it possible, and now, with the EP powered down, one part of that sensing is gone. The spacecraft can no longer measure the low-energy charged particles that were part of its portrait of this environment. It is not a catastrophic loss. Other instruments are still running. The mission continues, but the portrait is a little less complete, a little less detailed. One voice in the choir, now quiet. This is the nature of what is happening to Voyager 1. A gradual narrowing. The universe around it remains as vast, as full of things worth knowing as it ever was. But the spacecraft's ability to sense that universe, to translate it into data and send that data back to us, is slowly, carefully being reduced. What we are left with is still extraordinary. A machine launched nearly 50 years ago, still transmitting from beyond the solar system, still telling us things we did not know, but quieter than before, and getting quieter with time. There is something in that worth sitting with, not sadness exactly, something older than sadness. The feeling you get when you watch something remarkable begin to wind down, knowing that it will end, knowing that the ending is appropriate, knowing that what came before it was more than enough, and still finding it hard to look away. Consider what the interstellar medium actually is. It is the space between the stars. It is not empty, but it is extraordinarily thin. In the best vacuum scientists can create on Earth, There are roughly 10 trillion molecules per cubic meter in the interstellar medium. There are perhaps 1 million. A million sounds like a lot, but spread across the distances involved, it is as close to nothing as nature gets outside a black hole, and yet, in that near nothing, there are magnetic fields, fields that stretch across light years, fields that record the history of stellar explosions from millions of years ago, fields that carry the echoes of supernovae, stars that died before our sun was born, still propagating outward through the medium, slowly fading, but not yet gone. Voyager 1 moves through all of this. It is not just crossing mostly empty space. It is reading a library written in particles and fields across distances and timescales was not evolved to comprehend. And it is sending pages of that library back to us, one packet at a time, one signal crossing 15 billion miles at the speed of light every day for as long as it can. Every atom in the interstellar medium was once inside a star. The hydrogen that surrounds Voyager 1 was created in the first minutes after the universe began. The heavier elements, the carbon, the oxygen, the nitrogen, and iron and silicon, were forged inside stars over billions of years and released when those stars died. Some of them exploded as supernovae, some of them shed their outer layers into the space around them as they cooled and collapsed. All of that material eventually mixed into the interstellar medium, into the thin cloud of matter that fills the galaxy, the same cloud that Voyager 1 is now moving through, in a sense. Everything out there was once somewhere else. Everything that exists has a history stretching back to the beginning of the universe. The particles Voyager 1 is measuring, the ones the LCP was counting before it went quiet, those particles have been traveling across the galaxy for millions of years. Some of them came from supernovae in distant corners of the Milky Way. Some of them were accelerated by the shock waves of exploding stars and have been moving nearly at the speed of light ever since. And Voyager 1, a small machine from Earth, has been sitting in that stream, counting them, for nearly 5 decades. It is a remarkable thing to sit with. You are lying somewhere warm, somewhere safe, somewhere close to the surface of a planet that is itself hurtling through space, and far away, past all the planets you learned about in school, past the boundary of the solar system itself, a small gold and aluminum machine is still moving, still measuring, still sending. Let that thought carry you wherever you are going tonight. The SP will not be the last instrument to go quiet. Everyone who works on this mission knows that the power curve is predictable. Every year, the RTGs produce a little less. Every year, the engineers run the numbers again. Every year, the list of systems that can be sustained gets a little shorter. This is not a crisis, it is a process, a long, slow, carefully managed process of letting go. The next decisions have not yet been made. The mission team will continue to evaluate what remains. They will look at which instruments are still returning valuable data. They will look at which heaters are protecting the most critical systems. They will look at the transmitter, the one component that must remain on for as long as possible, because it is the only thing that connects Voyager 1 to us. The transmitter is the voice. Everything else serves the voice or is sacrificed for it at some point. In the years around 2030, or perhaps a little later, depending on how carefully the power is managed, The transmitter itself may no longer have enough energy to send a signal that Earth can receive, not because it breaks, because the power is finally simply not enough. When that happens, there will be a last signal, a last packet of data crossing the darks. The engineers will know it might be the last. They will be watching, and then, after a wait of about 23 hours, they will know for certain. No confirmation will come back. The dish will still be pointing at the right patch of sky. The signal will simply not be there, and Voyager 1 will continue flying. It will not stop. There is nothing to stop it. No friction, no resistance, no force acting against it. In the quiet of interstellar space in motion, in an object in motion, space in motion, Newton's first law, still true, still applicable. Even here, even now, even at the edge of everything, it will fly past the heliopause's far edge. It will move through the Oort cloud, the distant shell of comets, at the outermost edge of the sun's gravitational influence. That journey alone will take tens of thousands of years. Then it will continue into the space between stars, properly, finally interstellar. The signal will be gone. The mission, by any official definition, will be over, but the spacecrafts will still be there, moving, carrying everything it was sent with, including something placed on board before it launched, something that was never meant for the instruments, never meant for the engineers, never meant for us at all. Think about what it means to build something and then release it into the universe. Engineers design with specifications, with requirements, with margins of safety and expected lifetimes and defined mission objectives. Voyager 1 has outlasted every expectation by decades. The people who built it could not have imagined this. The engineers who first calculated Voyager's trajectory, who worked out the geometry of the Grand Tour, the rare alignment of outer planets that would not occur again for another 176 years. Those engineers could not have known that their spacecraft would one day be crossing into interstellar space. They were trying to reach Jupiter and Saturn, and they reached those targets and went far beyond them and kept going and are still going, quietly, in the dark. There is a lesson in that, not a lesson about spacecraft, about what happens when you do your work well, and then let what you have made become something larger than what you intended. You cannot always know where your work will go. You cannot always predict what it will become. You can only build it carefully, give it the best foundation you can, and release it into the world, trusting that the work itself will find its way farther than you expected. Voyager 1 did that. In the most literal way possible, before Voyager 1 launched, someone made a decision, not about the instruments, not about the trajectory, not about the power systems or the communication protocols or the backup thrusters, a decision about what the spacecraft should carry with it, in case it was ever found. Attached to the side of Voyager 1 is a gold-plated copper disc, 12 inches in diameter, about the size of a vinyl record. It is called the Golden Record. On it, encoded in a format designed to be decoded by any scientific knowledge, are sounds and images from Earth, the sounds of wind and rain and ocean waves, the sounds of animals, birds, a chimpanzee, the sound of a human heartbeat, a kiss, a mother speaking to a child, greetings in 55 languages, music from cultures across the world and across centuries. Bach, Beethoven, a Navajo night chant, Blind Willie Johnson, a Georgian choir, a Peruvian wedding song, and 115 images encoded in the grooves of the disc, showing the human form, human anatomy, the structure of DNA, mathematical notation, a nursing mother, a group of children, the surface of Earth from space. The golden record was not made for any of us, made for whatever or whoever might one day find this object drifting through the dark. It is a message in a bottle cast into an ocean with no shoreline. The chances that it will ever be found, let alone understood, are extraordinarily small. Carl Sagan, who helped design it, knew this. He called it a gift to the cosmos, not a practical communication, a gesture, a way of saying, we were here, we were curious, we looked outwards, we made something beautiful, and we sent it out, because that is the kind of creature. Voyager 1 will carry this record for longer than our species has existed, long after the last signal fades, long after the mission is declared complete, long after everyone who built it, who flew it, who spent careers listening to it, is gone. The record will still be there, the spacecraft will still be moving. In 40,000 years, it will pass within 1.6 light-years of a small red dwarf star, AC 793888, in the constellation Camelopardalis. No one alive today will be there to see it, but the record will still be on board, the heartbeat still encoded, the music still there, the kisses, the mother's voice, the crossing the dark between star 17 kilometers per second in the direction of something that, as far as we know, that as no one is waiting for it, and yet it goes, because that is what was decided in 1977 when someone thought to ask, what should we send in case someone finds this? And the answer was, everything we could fit, everything worth saving, everything worth sharing, the best of what we are. The golden record contains a diagram of the solar system showing which planet this spacecraft came from. It contains a pulsar map, a way of locating our sun by triangulating the position of 14 pulsars whose frequencies are known. Any civilization advanced enough to intercept this spacecraft would, in theory, be able to find Earth. Some people find that unsettling. Carl Sagan did not. He argued that any civilization capable of finding Voyager would already be far more advanced than we are. The idea that we might be giving away our location, he felt, was thinking too small. Better to say hello, better to share what we have made, better to leave something behind that tells the truth about who we were. The golden record tells that truth, not a propaganda version, a genuine attempt to capture what it was like to be alive on this planet in this moment of our history. The sound of a string of laughter, the sound of a string quartet playing something beautiful. Afternoon, all of it encoded, all of it spinning through the dark at 17 kilometers per second, all of it waiting. The committee that chose what to include on the golden record debated many things. They wanted to represent the full breadth of human culture, not just Western culture, not just modern culture, but as many voices as they could fit on a 12-inch disc. They chose music that would not translate easily into words, music that communicated something about what it feels like to be human, the particular quality of emotion and structures and sound that we create when we are trying to say something that language alone cannot carry. They chose greetings in 55 languages because they wanted whoever might find it to hear the diversity of human sound, the different ways our vocal cords shape the air into meaning. They chose images carefully, geometric and mathematical diagrams first, as a kind of shared language that any sufficiently advanced civilization might recognize, and then images of life, of the planet, of human bodies and human faces. They put a child's drawing on the golden record, a simple drawing, the kind a young person makes when asked to capture something about the world they live in. It is theirs, encoded in the grooves, traveling through the dark, along with Bach, along with the sound of rain, along with the heartbeat, all of it together, all of it Voyager 1, still carrying it forward. There will come a day when the engineers at JPL send a command to Voyager 1, RERM, and wait, and no answer comes back, not because something went wrong, because the power was finally quietly not enough. They will wait longer than usual. To be sure, they will try again. They will check the calculations. They will verify the antenna pointing. They will rule out interference, equipment issues, anything explainable, and then, at some point, the conclusion will become unavoidable. As the signal is gone, Voyager 1 will have joined a very small list of objects, the most distant things humanity has ever made, that we can no longer hear. The mission will be declared over. There will be statements, perhaps a small ceremony. People who spent decades on this will gather somewhere and acknowledge what has ended, and then they will go home, and Voyager 1 will keep flying through the Oort clouds, through the outer reaches of the sun's gravitational influence, into the space between stars, carrying the golden record, carrying the memories of the people who built it, carrying in some sense the ambition of an entire species at a particular moment in its history. It's a moment when we decided to send something outward, not because we knew what we would find, but because we were the kind of creature that needed to look. Voyager 1 will not know because we were not, that the signal has ended. Spacecraft do not know things. It will simply continue doing what it has always done, flying, measuring for as long as it can, carrying the record, moving through the dark at 17 kilometers per second, a small gold disk in an enormous silence, farther every second than the second before. In 40,000 years, it will pass near a star. In millions of years, if it survives, cause it will be somewhere we cannot imagine. Tonight, it is close enough that we can still talk to it. Close enough that a signal sent from this planet, from the people watching over it, can still reach it. In less than a day, that will not always be true, but it is true now, and for now, that is enough. The universe is very old and very large and mostly very quiet, but somewhere out there, past the edge of the solar system, past the boundary where the sun's influence ends, a small machine is still moving, still transmitting, for now, still reaching back across the dark toward the planet that made it. And here it's on that planet, just like this one. People are lying in the dark, listening. That is something, a small machine and a group of people still in conversation across a distance that almost cannot be imagined, still connected, still exchanging, in their slow and careful way, the quietest possible version of hello and I am here. When the signal finally ends, it will not end with drama. It will end the way most things end. Then quietly, then simply not at all. The engineers will note it. The records will be updated. the mission will be closed and Voyager 1 will keep going, because that is what it does, because that is what it has always done, because there is nothing in interstellar space to tell it to stop. The signal will end, but the journey will not. Rest now. The spacecraft is still flying, and you, wherever you are tonight, are part of the same universe it is crossing. You are made of the same matter that fills the interstellar medium moves through. The hydrogen in your body was created in the first minutes after the universe began. The carbon and oxygen were forged inside stars that died before our sun was born. You are, in some small and accurate way, connected to everything Voyager 1 has ever passed, ever measured, ever sent back to us, connected to the cold of interstellar space, connected to the ancient light of distant stars, connected to the long, slow work of physics and time that built everything that exists. Sleep well. The dark is very large, but it is not empty, and neither are you. The spacecraft is still flying. Somewhere beyond the last planet, beyond the boundary of the sun's reach, past the edge of everything we have explored, it is still moving, still carrying its record, still crossing the quiet, and tonight for a little while longer, it is still sending, still saying the only thing it has ever said. I am here, I am still here, I am still going. The story of Voyager 1 is also the story of a particular era in human history. The 1970s were a decade of extraordinary ambition in space. The Apollo program had ended, the moon landings were over, but the knowledge gained, the engineering knowledge, the organizational knowledge, the keta, sheer accumulated experience of sending human beings beyond the atmosphere, that knowledge did not disappear. It transformed. It moved into robotic spacecraft, into machines that could go farther and last longer and survive conditions that no human body could. Voyager 1 was part of that transformation. It was designed by people who had learned from Apollo, who had learned from Mariner, from Pioneer, from a decade of missions that failed and succeeded and taught. They brought all of that learning to bear on a spacecraft that would take advantage of a once-in-176 years opportunity. The outer planets, Jupiter, Saturn, Uranus, Neptune, aligned in a configuration that would allow a single spacecraft to visit all four, using each planet's gravity to accelerate toward the next. A gravitational slingshot. Each planet passed close to would add speed to the spacecraft, essentially borrowing momentum from a planet's orbital motion and transferring it to the probe. The engineers who calculated this trajectory called it the Grand Tour, and they knew they had a narrow window. If the mission did not launch by the late 1970s, the alignment would pass and would not return for another century and a half. So they launched Voyager 1 first, then Voyager 2 a few weeks earlier. A different trajectory, aimed at different targets, and they went into the dark toward the outer planets, toward everything beyond. The people who launched them could not have known that both spacecraft would still be operating nearly 50 years later. They could not have known that Voyager 1 would become the first human object to leave the solar system They were doing what engineers do. They were solving the problem in front of them, using the tools they had, doing their best work, and letting that work become whatever it was going to become. There is a lesson in that, not a dramatic one, not a lesson that fits on a poster, just this. Sometimes, if you do careful work, and you are patient, and you take care of what you have made, it will go farther than you ever expected, farther than you can imagine, farther than anyone thought possible. That is what Voyager 1 has done, and it is still doing it right now. Tonight, the engineers who built Voyager 1 in the late 1970s used the computing technology of that era. Voyager 1's onboard computer has less processing power than a modern digital watch. It operates in binaries. It stores data on an 8-track tape recorder. The original memory holds only about 70 kilobytes of data, less than a single photograph taken on a modern phone, and yet this machine, with its tiny memory, its ancient tape recorder, its 1970s computing architecture, has outperformed every expectation. It has operated continuously. For nearly 50 years, it has survived temperatures close to absolute zero. It has functioned in an environment, cosmic rays, interstellar plasmas that no one fully understood before Voyager entered it, when engineers discovered in 2023 that Voyager 1 was sending garbled data, that something in its onboard computers had gone wrong. They faced an extraordinary challenge. The spacecraft was more than 15 billion miles away. Every command took 22 to 23 hours to arrive. Every response took another 22 to 23 hours to return. And the engineering documents for the spacecraft, the technical manuals, the circuit diagrams, the code documentations were nearly 50 years old. Some of the engineers who understood the system best were no longer alive. The team at JPL spent months working through the problem. They examined old documentation, they ran simulations, they sent careful, targeted commands, and waited 2 days for each response. And then, in April 2024, they found the cause: a single corrupted chip. In one section of the computer, they found a workaround. They stored the affected code. In a different part of the memory, they sent a series of commands. They waited, and Voyager 1 came back. After 5 months of garbled data, it began transmitting clearly again. It had survived. The team had saved it. This is the story of Voyager 1. Not just the instruments, not just the distances, but the people, the ones who have been watching over it for nearly half a century, who have refused to give up on it, who have found over and over again ways to keep it going a little longer. The data that comes back from Voyager 1 travels at the speed of light. That sounds fast. Light travels at about 300,000 kilometers per second. In 1 second, light can circle the entire Earth 7.5 times. In 8 minutes, light travels from the Sun to the Earth in about 4 hours. Light reaches Neptune, the most distant planet in the solar system, and yet it takes about 23 hours for light to reach Voyager 1. That is how far it has gone. beyond Neptune, beyond the Kuiper Belt, beyond the heliopause, into interstellar space, where even light, the fastest thing in the universe, takes most of a day to arrive. When the signal from Voyager 1 finally reaches Earth, it arrives at the Deep Space Network antennas as an almost incomprehensibly small amount of power. The receivers that detect it must be cooled to temperatures close absolute zero, not because they are in space, they are on Earth, in the desert, but because thermal noise, the random movement of electrons caused by heat, would overwhelm the signal if the receivers were not kept cold. The signal from Voyager 1 is so faint that the natural heat of room temperature entirely. It requires extraordinary technology just to hear it. And yet, every day the team listens, every day the signal arrives, and the quiet confirmation Voyager 1 is still there. Think about what that means for the people whose job it is to listen. They come to work, they check their instruments, they wait for the signal to arrive, and then they receive it. This tiny, ancient whisper from the edge of the solar system, and they know that it is still out there, that the work they do matters, that the spacecraft they have spent years or decades caring for is still flying. That is not a small thing. There is a kind of satisfaction in it that is hard to describe. To someone who has not experienced it, the satisfaction of being responsible for something extraordinary, of being part of a chain of care that stretches back decades, to the engineers who built the spacecraft, to the mathematicians who calculated its trajectory, to the scientists who designed the instruments, Krumpf and forward into a future that none of us will fully see. The engineers at the Deep Space Network are part of that chain. Every day they come to work. Every day they listen, and Voyager 1 keeps talking. For now, the heliosphere is not a perfect sphere. Scientists once thought it might be roughly spherical, a bubble expanding outward in all directions from the Sun, but measurements from Voyager 1 and Voyager 2, which crossed the heliopause at different points and at different distances from the Sun, suggested the shape is more complex. The heliosphere may be elongated, stretched in the direction of the Sun's travel through the galaxy, and compressed on the other side. Imagine a comet's tail, that long, glowing extension pointing away from the Sun. The heliosphere may have something like that, a long tail extending in the direction opposite to where the Sun is heading, and a compressed bow on the leading edge where the solar wind pushes against the interstellar medium more forcefully. Scientists are still working this out. The shape of the heliosphere is one of the things that only direct measurement can fully settle, and the only spacecraft with direct measurements are Voyager 1 and Voyager 2's two probes launched 16 days apart, taking different paths through the solar system, crossing the heliopause at different latitudes. Together, they give scientists 2 data points from which to infer the shape of the boundary that surrounds our entire solar system, 2 data points from the most sophisticated instruments we could design in 1977. It is enough to learn something. It is not enough to learn everything. That is the nature of exploration at the frontier. You send what you can, you learn what you can, and you wait for the next mission, the one that will build on what you found, to tell you more. For the heliosphere, that next mission has not yet launched. Voyager 1 and Voyager 2 remain the only direct sources of data from interstellar space. When they go quiet, there will be no others, not for many years, perhaps not for decades. The window that these two spacecraft opened onto the universe beyond our solar system, that window will close, and what they managed to show us while it was open will be what we have. That is one reason why every data packet still matters. Every reading from every instrument still running, every faint signal because still making the crossings. Each one is a piece of a picture that will not be added to for a very long time. The interstellar medium is not uniform. It has regions, neighborhoods. In a sense, our solar system sits inside what astronomers call the local bubble, a large region of space that was carved out by a series of supernova explosions. Approximately 2 million years ago, stars exploded. Their shock waves pushed the surrounding gas outward, creating a cavity, a region of lower density and higher temperatures than the average interstellar medium. We live inside that cavity. Our sun has been traveling through it for millions of years. The edges of the local bubble are regions of denser gas and dust, the remnants of what was pushed aside by those ancient explosions. Voyager 1 is just barely into the local interstellar medium, the region just outside the heliopause, still inside the broader local bubble. It will remain in this region for tens of thousands of years, far longer than any signal it sends will be detectable, far longer than our civilization will exist in its current form. The local bubble itself extends for several hundred light years. In most directions, to cross it entirely would take Voyager 1 roughly 2 to 3 million years. And beyond the local bubble is another region, RB, and another, each one shaped by the explosions and movements of stars over billions of years of galactic history. The Milky Way is not a uniform disk of stars. It is a complex, layered environment of gas and dust and magnetic fields and cosmic rays and stellar remnants and empty space that range from the width of a planet to the width of the galaxy itself. Voyager 1 has barely scratched the surface of that environment. It has traveled, in cosmic terms, an almost infinitesimally small distance, and in that small distance, that barely begun journey, it has already overturned assumptions, revised models, and told us things we did not know. What the full journey would reveal, as if something could complete it, is beyond imagination. But we are not yet at the point where we can send something that completes that journey. We are still at the beginning. We are Voyager 1 is the first step, a small step, a step taken with 1970s technology and a lot of human patience and care, but a real step, the first. And tonight, it is still taking that step, still moving, still sending. The history of Voyager 1's power management is a history of difficult choices, panned, Made carefully and quietly over many years, the first instrument was turned off in 1990. The cameras, after the famous pale blue dot image, the photograph of Earth from 6 billion kilometers away. Carl Sagan had argued for pointing Voyager's cameras back toward the solar system to get a family portrait to see for the first time all the planets of our solar system from outside. They did that. The images were taken, the pale blue dot was captured, and then the cameras were turned off because they were power-consuming instruments that were no longer scientifically essential for where Voyager was going. The heliosphere and interstellar space are not regions where cameras would reveal much. The science of those regions is in particles and fields and waves, not invisible light. So the cameras went dark, the first instruments to be turned off after systematic power management began were deactivated in the 1990s, then more in the 2000s, then more in the years that followed. Each time, the same careful process, the same assessment of what the spacecraft needed, the same calculation of what could be spared, the same quiet command sent across billions of miles, and the same long wait for confirmation, the same moment of letting go. Voyager 1 in 2026 is a different spacecraft than Voyager 1 1977, not in its structure, not in its trajectory, not in its fundamental systems, but in its capabilities. It sees less now than it once did. It senses less, it reports on fewer things, and still it flies, still it transmits, still it carries its record into the dark. There is something about the way Voyager 1 has aged that feels familiar, not because spacecraft age like people, they do not, but because the pattern of gradually losing capabilities while the essential core continues, while the fundamental drive to keep going persists. That pattern resonates. We recognize it. We have seen it in the people we have loved and cared for, in the things we have built and maintained, in ourselves. Perhaps, if we are paying attention, the capacity to continue, to keep doing the essential thing, even as the surrounding capability. That is what Voyager 1 is doing, continuing, doing the essential thing, flying. For as long as it can, the golden record is often described as humanity's message to the universe. But that framing misses something. It is also a message to ourselves, a record of what we chose to say when we imagined being seen by someone who did not already know us. What do you put on a record meant for unknown eyes and ears? You put the things that you believe are most true about what you are. The things that if you could say only one thing or 100 things about human civilization, you would want to say, and what the golden record says in its combination of sounds and images and mathematical diagrams and musical selections is something like this. We are curious, we make patterns, we feel things, we have found ways to convert those feelings into sound and image, and we call that art. We have found ways to describe the structure of the universe in mathematics, and we call that science. We live on a wet blue spinning world that is by all current evidence cunty, extraordinarily rare. and we are aware enough of our own rarity to want to share it. That is what the Golden Record says, in the sounds of surf and rain and heartbeats, in the music of Bach and Louis Armstrong, in the greetings in 55 languages, in the image of a nursing mother, in the drawing of a child, in the photograph of Earth from space, small and bright and utterly alone in the dark. The record will outlast everything else about Voyager 1. When the last instrument goes quiet, the record will still be there. When the transmitter finally falls silence, the record will still be there. When the spacecraft has been flying for longer than our species has existed, the record will still be there. Gold does not decay quickly. Copper does not decay quickly in the vacuum of space. Reactions that oxidize and corrode material on Earth. The disk could remain intact for billions of years, billions, longer than the Earth has existed, longer than the sun will burn, just a disk spinning through the dark, carrying its encoded message, waiting, perhaps never to be found, perhaps to be found by something we cannot imagine, perhaps to be found by a civilization that arose on a world around a star that does not yet exist. Because that star has not yet been born, we do not know, we cannot know. What we can know is this: we made it. We put it on the spacecraft, we launched it into the universe, and it is still out there, still going. That is something. The Oort cloud, which Voyager 1 will eventually enter, is not really a place you can see. It is a theoretical region inferred from the orbits of long-period comets that fall into the inner solar system. From scientists believe it extends, scientists 2,000 to extends from roughly 2,000 to 100 astronomical units from the sun, from about 300 billion to 15 trillion kilometers. Voyager 1 will not reach the inner edge of the Oort cloud for another 300 years, and it will not fully emerge from the far edge for perhaps 30,000 years. The Oort cloud is the outermost part of the solar system, the farthest extension of the sun's gravitational influence. Beyond it, the sun is just a star among stars, not a gravitational anchor, not a source of warmth, not a center, just one of hundreds of billions of suns in the Milky Way. And Voyager 1, after it leaves the Oort cloud, will be in interstellar space, in the fullest sense, between the influence of two stars belonging to neither, moving through the galaxy on its own path, governed only by the combined gravitational influence of the Milky Way as a whole. A small machine, an extraordinary traveler, a carrier of records, moving through the dark for as long as the dark goes on, and the dark goes on for a very long time. The Milky Way is roughly 100,000 light years across. At Voyager 1's current speed, crossing it end to end would take roughly 1.7 billion years. Long after the sun has exhausted its fuel, long after the Earth in its current form is gone, long after anything we currently call human civilization has transformed into something unrecognizable. The universe will still be here. The stars will still be burning, or their successors will be burning. New stars, formed from the remnants of old ones, and Voyager 1 will still be moving, still carrying the golden record, still crossing the quiet with the sound of a heartbeat encoded in its grooves. That is one of those facts that is too large to really hold. You can say it. You can understand the individual words, but to feel the full weight of it, to truly inhabit the scale of what it means, that is beyond what a human mind can really do. And perhaps that is all right. Some things are meant to be sensed, not fully understood. Some things are meant to be held lightly, like the knowledge that the universe is vast and we are small and we have done something extraordinary anyway. Rest in that, let it carry you. The spacecraft is still flying, you are still here, both of you in your different ways, still moving through the dark between Jupiter and Saturn. There is a distance of about 650 million kilometers. Voyager 1 crossed that distance. In roughly 20 months, it flew through a region of the solar system. Where the sun was smaller than you might expect. Not the brilliant disk we see from Earth, but a bright point of light, noticeably brighter than any star, but no longer a sun the way we know it. For 20 months, it flew in the direction of Saturn, adjusting its trajectory, checking its instruments, sending data home. Those 20 months were not dramatic. Nothing went spectacularly wrong. Nothing went spectacularly right. The spacecraft simply flew, day after day, kilometer after kilometer, signal after signal. This is most of what space travel is. Not the moments of discovery, not the flybys and the photographs, and the unexpected revelations. Most of it is just flying, just the long, patient work of crossings a very large distance at a speed that feels fast by human standards and slow by cosmic ones. Voyager 1 was good at that. It is still good at that. After nearly 50 years, it is still doing the same thing it always did, flying patiently through the dark. In 1990, Voyager 1 turned its cameras back toward the solar system and took a series of photographs. These Carl Sagan called into what Carl's solar system, a view of our solar system. From outside, 6 of the 9 planets were visible. Mercury was too close to the Sun, Mars was too dimly lit, Pluto was too small, but Jupiter, Saturn, Uranus, Neptune, Venus, and Earth, those 6 appeared, small, bright points of light against the black, and among them, barely visible, a pale blue dot. That was Earth. That was us. Carl Sagan wrote about this photograph in a way that has been quoted many times since. He wrote about the rivers of blood, the cruelties we commit in the name of nations and gods, because the conquests and wars and empires, all of it happening on that pale blue dot. He wrote about the fragility and the loneliness and the uniqueness of the world we live on. And he wrote about the responsibility it implies. If this is our only home, if there is nowhere else to go, no backup planet, no second chance, then what we have here matters enormously. And how we treat each other and how we treat this world matters equally enormously. The pale blue dot photograph was not planned. As a scientific instrument, it was not designed to return data that would advance our understanding of physics or chemistry or planetary science. It was planned as a gesture, a way of seeing ourselves from the outside, of understanding visually and viscerally where we actually are. In the You Worked, that image, that small, faint dot, has become one of the most famous photographs in human history, and it was taken by Voyager 1, the same spacecraft that is now being quietly shut down, one instrument at a time. The three complexes of the Deep Space Network, Goldstone in California, Madrid in Spain, Canberra in Australia, are spaced roughly 120 degrees apart around the globe. This is deliberate. As the Earth rotates, each complex takes its turn, pointing toward the distant spacecraft. When Goldstone sets below Voyager 1's horizon, Madrid is rising. When Madrid sets, Canberra is rising, and so on, around and around, day after day, for nearly 50 years. This arrangement means that Voyager 1 is never out of reach for more than a few minutes at a time. There is always an antenna somewhere pointed in its direction, always listening, always ready to send or receive. The Deep Space Network was designed this way from the beginning. The engineers who built it understood that if you were going to send something into deep space and rely on it for data, you could not afford to let it go unheard. You needed coverage, continuous, redundant, around-the-clock coverage, and they built it. They built 70-meter dishes in 3 countries. They kept them operational for 5 decades. They trained new generations of engineers to listen for old signals. They maintained the infrastructure of a conversation that has been ongoing. It's 1977. That is an extraordinary institutional commitment, the kind of thing that rarely gets celebrated. It's the ways, the photographs, the way the launches do, or the photographs, or the discoveries. But without it, none of the rest would be possible. The dishes pointing at the sky, the engineers checking their instruments, the signal arriving, decoded, interpreted, understood every day. For nearly 50 years, the heliopause is not a fixed boundary. It breathes in its own slow way. The sun's activity cycles over roughly 11 years, from solar maximum, when sunspot activity and solar wind are strongest, cut to solar minimum, when they weaken. As the solar wind strengthens and weakens, the pressure it exerts on the surrounding interstellar medium changes, and as that pressure changes, chiefly the boundary of the heliosphere, the heliopause, expands and contracts slightly, not dramatically, not by billions of kilometers, but measurably. The heliosphere breathes to the rhythm of the sun's activity, and inside it, the planets, including Earth, are protected. The heliosphere shields us from the full intensity of the galactic cosmic ray environment. Without it, the radiation reaching Earth's surface would be significantly higher. Life as we know it may depend on this protection. The heliosphere is not just our solar system's outermost boundary. It may be part of what makes Earth habitable, one of the many layers of protection. The atmosphere, the magnetic field, the heliospheres that together create the conditions in which life can exist. Voyager 1 has helped us understand this protection by crossing through it, by measuring the transitions, by sending back data from the region where protection ends and the full force of the galaxy begins. That knowledge has value for understanding where we live, for understanding how we are shielded, for understanding what makes this solar system and perhaps others capable of hosting life. There is a thought experiment worth trying as you drift towards sleep. Imagine you are floating, not in water, not in air, in the interstellar medium, in the region of space that Voyager 1 now occupies. The temperature around you is only a few degrees above absolute zero, but you are not cold. This is a thought experiment, and you are imagining, not experiencing. You are simply there, floating in every direction as far as you can see. There is darkness and stars, not the stars of Earth's night sky, not the warm, familiar constellations we grew up with. These stars are different. The sun is behind you, or to one side, still brighter than any other star, but diminished, a bright point, not a sun, in the direction Voyager 1 is heading. There are other stars, dim, distant, ancient, each one a sun, each one potentially surrounded by worlds we will never visit. The galaxy spreads around you in every direction, not empty, full of matter and energy and history. The history of billions of stars over billions of years, all of it here, all of it now, surrounding you in the dark, and then very close to you, close enough to touch. If you stretched out your hand, a small machine, gold and aluminum, dish antenna pointing toward a distant sun, RTGs glowing faintly with the warmth of decaying plutonium. Voyager 1, still moving, still transmitting, still faithfully sending its report home. You float there for a moment, in the interstellar medium, in the place between stars, in the quiet that is not empty, and then you let the thought go, let it carry you down toward whatever comes next. The spacecraft is out there, the darkness is vast, and you are here, safe, warm, still on a small blue world at the edge of the Milky Way. There is a kind of sadness in watching something wind down, even when the winding down is appropriate, even when it was always going to happen, even when the thing itself has far exceeded every expectation. There is still something in us that wants it to continue, that wants the signal to keep coming, that wants the instruments to keep measuring, that wants the data to keep arriving. Because as long as the signal comes, we are connected to something we put into the universe, connected to the edge of the solar system, connected to the dark beyond. When the signal ends, that connection ends, and we will not be able to make it again. Not this connection, not with this spacecraft. For as long as any of us are alive, that is worth acknowledging, worth sitting with, not in a spirit of grief exactly, more in the spirit of being present for something, of not looking away. The engineers who will hear the last signal, who will be there in the control room, watching the data stop arriving, they will be present for something that will not happen again. The end of a mission that has lasted nearly half a century, the last communication with the most distant object humanity has ever made, the moment when the conversation that began in 1977 finally goes quiet. There will be sadness in that moment, And there will be something else too, something that is harder to name, the particular feeling you get at the end of something that was genuinely great, not just loss, not just grief, but the recognition that what came before the ending was worth it, more than worth it, that the distance covered, the discoveries made, the records carried forward, all of it was more than anyone had any right to hope for. The ending does not diminish what came before, it completes it. The people who chose what to put on the golden record had to make difficult decisions. There was limited space. A 12-inch disc can hold only so much data. Every choice meant leaving something else out. Every piece of music selected meant 100 others were not. Every language represented in the greetings meant dozens of others were absent. They tried to be representative. They tried to be honest. They tried to choose things that would communicate something true about the breadth of human experience. But they were working in 1977 with the knowledge and perspectives, with the knowledge and available in 1977 with the biases and blind spots of their particular moment in history. The choices made, archivist S, that Western music is overrepresented, that certain cultures were ignored, that the selection reflects the limitations of its creators. Those criticisms are fair, and they are also, in a way, reassuring because they remind us that the golden record is not perfect. It is human. It was made by people doing their best with the time and resources and knowledge they had. It's just like Voyager 1 itself, just like all of the things we make and send out, not perfect, but genuine, but real, but made with care. And now traveling through the dark at 17 kilometers per second, carrying all of its imperfections, along with all of its beauty, the way most human things do. Tonight, as you settle towards sleep, there are few things that are true. The universe is very large. The distances inside it, air so enormous that they defeat ordinary imagination. And in this universe, in this almost incomprehensible vastness, we have sent something out, a small machine, no bigger than a car, carrying instruments that measure particles, carrying a transmitter that whispers homeward, carrying a record of what we are and what we value and what we find beautiful. And it is out there right now, moving through the dark and sending its signal, receiving our commands, flying in the direction of elsewhere. This is an extraordinary thing, not because the distances are large. They are not because the technology is impressive, it is, but because someone in 1977, I looked outward and decided to go, not in person, not with any certainty of discovery, not with any guarantee that the missions would succeed, just with curiosity, with care, with the willingness to try, that impulse to look outward, to send something beyond what is known, to say hello to the universe and see what comes back. That impulse is one of the things the golden record is trying to capture, not as a boast, not as a declaration of achievement, but as a statement of who we are. We are the kind of creature that looks at the stars and wants to know more. That is not nothing. That is, in fact, one of the most remarkable things about being what we are. Rest in that. Let it be the last thought. Before sleep comes, the spacecraft is still flying. The signal is still traveling. The universe is very large, and we are small inside it, and we are still reaching out. There is a practice in the listening, not just the technical practice, the calibrations, the calculations, the careful tuning of enormous instruments to receive something almost too small to detect, but a different kind of practice, a practice of attention, of showing up, of being the ones again today, who point the dish at the sky and wait for what comes back. Some of the engineers who work on Voyager today were children when it launched. Some were not yet born. They learned about the mission from documents, from older colleagues, from the accumulated record of everything that had been done before them. They stepped into a role that had been held by others, who had held it from others, who had held it from the people who built the spacecraft in the first place. A chain of care across nearly 50 years, across the careers of multiple generations, the same spacecraft, the same signal, the same quiet work of listening and interpreting and sending back instructions, different hands on the same instruments, different eyes reading the same data streams, different minds working through, the same that their predecessors solved or left unsolved or passed along. This is what it means to maintain something over a very long time. Not just the technology, the knowledge, the attentions, the commitment to keep showing up. As long as Voyager 1 is sending, someone will be listening. That is the promise that has been kept for nearly 5 decades, and it is being kept tonight, right now, as you read this, as you breathe, as you move towards sleep. Somewhere, an antenna is pointing at the sky. Someone's watching the data stream. Someone is doing the quiet work of staying connected to the most distant thing we have ever made. When Voyager 1 crossed the heliopause in August 2012, scientists were not immediately certain it had happened. The crossing was not clean. There was no single moment when the instruments registered a sudden shift and everyone in the control room stood up and cheered. Instead, the data came in, the numbers were analyzed, the models were consulted, the debate began. Some scientists looked at the data and said, the magnetic field has changed direction, the particle density has increased, the solar wind has gone quiet, it has crossed. Others said, it's not so fast. The data is ambiguous. There could be other explanations. We need more observations. The debate went on for months. Papers were published. Responses were written. The data was reanalyzed, and eventually a consensus formed. Voyager 1 had crossed the heliopause. It was in interstellar space. For the first time in history, a human-made object was outside. The sun's protective bubble. The announcement was made in September 2013, more than a year after the crossing, not with immediacy, not with a live event or a countdown, with careful science, with measured confidence, with the kind of deliberate certainty that comes from checking your work many times. This is how science actually works. not with flashes of insight and moments of sudden clarity, or not only with those things, but with slow, careful accumulation of evidence, with debate and revision and consensus, with the willingness to say, I think this is true, and to keep checking until you are confident enough to say, I believe this is true. Voyager 1 taught us many things about interstellar space. It also taught us something about how we learn about the patient's required to do science at the frontier, where the data is ambiguous, where the models are incomplete, where the right answer is not immediately obvious. That patience is a virtue, one worth cultivating, one worth practicing, even here, even now. Even as you move towards sleep, there is a version of the golden record that has never been heard by anyone who was not present at its creation, a version experienced not as a familiar cultural touchstone, not as the thing you have read about or heard described, but as it might be received by something that had no context for it. No knowledge of what music is, no knowledge of what language is, no framework for understanding what a heartbeat means, or what a kiss sounds like, or why these particular sounds were chosen over all other sounds. Imagine receiving this disc, decoding its physical structure, understanding that it encodes information, developing the playback mechanism described on the cover, and then listening for the first time to 116 minutes of sound from Earth, to the sounds of wind and rain and surf, to greetings in 55 languages, to music that spans continents and centuries, to a heartbeat, to a mother's voice. What would you make of it? Captains, what would any mind make of it, hearing it without context? We do not know, we cannot know. The golden record was made as a gesture, not with any confident expectations of being received or understood, but the fact that it exists, that it is out there, that it continues crossing the dark. That says something, not about the universe, about us, about the kind of hope we are capable of, the kind that sends a message, knowing the message may never be received, the kind that encodes a heartbeat, knowing no other heart may ever hear it, the kind that says hello to the universe with no certainty of a reply. That hope is worth carrying with you into sleep, into tomorrow, into whatever comes next. The spacecraft is still flying, the record is still there, and the gesture, the act of reaching out, that will never be undone.